In this video, I'm going to provide a solution to the rotational motion quiz that we took recently, and so I would advise that you have that quiz out and make some corrections as you follow along and see how your solution compares to the one that I'm giving here. So that way, if you make those corrections, then your quiz is something that you can study from later on. And so I'm going to start by drawing an inclined plane, because in this problem we had different objects that were being released from the top of an inclined plane. In particular, there was a solid sphere, a hollow sphere, and a block of ice. The hollow sphere and the solid sphere were released from the top of an inclined plane where there was friction between the spheres and the plane, and then the block of ice was released from a different inclined plane, but from the same height at the same angle. So what I've drawn here is the solid sphere at the top of the inclined plane, inclined at an angle theta, and Part A says to derive an expression for the acceleration of the center of mass of the solid sphere that only depends on g and theta. The moment of inertia of the solid sphere is given. It says the moment of inertia is 2/5 mr squared. And so we can assume that the solid sphere has just a generic mass m and radius r. And when released, it's going to have an acceleration that points down the ramp like this. And we need an equation for that acceleration that only depends on g and theta. When I'm asked to find an expression for an acceleration, the first thing that comes to mind is Newton's second law. When I write Newton's second law, I already have an equation that has an acceleration in it, and since that's what I'm being asked to find, then that's a good place to start. And if I have an equation with Newton's second law, then I need to know all the forces that are acting on the object, so that way I can plug them into Newton's second law and solve for the acceleration. When I look at the solid sphere, I know that there's two forces that act on this solid sphere that are of importance to me. The first one that's important to me is the fact that there's friction that points up the inclined plane here. In addition to knowing that there's friction that points up the inclined plane which opposes the acceleration of the object, I also know that it's static friction. It's static friction because it rolls without slipping, and so it doesn't slide as it goes down the inclined plane. And there must be then static friction between those two. Which also means then, if it's static friction, then that frictional force doesn't do any work to slow down this object. Only kinetic friction can do that, only when they're sliding. So there's static friction there that points up the ramp. Then I have a gravitational force which acts at the center of mass, and it points straight down, and that could be labeled mg. But the component that I'm more interested in is the component of mg that points along the direction of the ramp, which is along the direction of the acceleration, and would be included in the net force equation that I'm trying to write on the right hand side. And so that component would be this part of mg, the part that's parallel to the ramp, and that component would be mg sine theta. In addition to those two forces, there's another force that acts on the solid sphere at the contact point between the surface and the sphere there, and that would be the normal force, which is perpendicular to the surface. But similar to the gravitational force, I'm not so worried about that normal force because it doesn't point along the direction that I'm solving for here with the acceleration and the net force parallel to the plane. So for that reason, I'll take those two forces in red and I'll plug them in to my net force equation, which is going to be for parallel to the plane. If I let down the plane be positive, then my force equation looks like this. mg sine theta is positive, so I write mg sine theta minus fs, it points up the ramp so it's negative, equals m times a, and since a points down the ramp, it's also positive. And when you get here, you should be at a point as a student where you should be asking yourself, where should you go next and what's leading me along the way? My solution is allowed to have g and theta in it, so on the left hand side that term's mostly okay. On the right hand side I have an acceleration there, which is what I'm looking for. And you see a couple of m's already, so maybe the m's are going to cancel soon. But one thing that definitely needs to be removed is this static friction term. I'm not allowed to have it in my final answer, and it doesn't look like anything's going to cancel with that yet. And so I need to write another equation which has static friction in it, so that way I can cancel those variables. The way that I'm going to take care of that is now by writing Newton's second law for the rotation. So F equals ma is for the translational motion from point A to point B, from the top of the ramp to the bottom of the ramp. But the net torque equals I alpha is Newton's second law for the rotation of this solid sphere. And so you have to ask yourself now, what forces are causing torques on this object? The gravitational force, either mg or the component that I've drawn in red, both act at the center of mass of this object, which is the axis of rotation. And since the force is acting at the axis of rotation, it can't cause a torque. Just like we've said before, it's kind of like me pulling or pushing on the hinges of a door. That's the axis of rotation. I can't cause the door to rotate by exerting a force there. The normal force doesn't act at the axis of rotation, acts a certain distance away. It acts at the contact point between the surface and the plane, or excuse me, between the sphere and the plane. But even though it acts a certain distance away, which would be the radius of that sphere, it still points toward the axis of rotation. In other words, it points along the direction of r, that moment arm, that lever arm that describes how big the torque is going to be. It points toward the axis of rotation, and so it also cannot cause a torque. The only force that causes a torque is the static friction force. And if you remember that the equation for any single torque is torque equals Rf sine theta, then we need to know how far is this force away from the axis of rotation. Well, that's just the radius of the solid sphere, which is capital letter R. The force that's being applied is the static friction force, Fs. And the angle between those two, I'm going to draw the angle here in green, is 90 degrees, right? R points along this yellow line that I'm adding, and the frictional force is perpendicular to that. And the sine of 90 degrees is 1, and so I can just write R times Fs times 1, which I don't need to write for the torque on the left-hand side. Since that's the only torque, I continue by writing equals. I is the moment of inertia of the solid sphere, which was given in the problem, which is 2/5 mr squared. And then alpha is part of this equation as well. Since I'm solving for the linear acceleration of the center of mass of this solid sphere, then I'm not looking for alpha. Similar to Fs, the static friction force, alpha is just an added variable that I'd really like to get rid of. The way that I'm going to get rid of that is by relating alpha into a, the linear acceleration. And those two variables are related in the following way, right? A equals R alpha. And so if I make this substitution, then I get Rfs equals 2/5 mr squared, and then substituting in for alpha, I can write A over R, A divided by R. And so now what you should see is that all of the r's are going to cancel. If I multiply both sides by r, I'll get to move that r out of the denominator. I'll have an r squared on the right, and I'll have an r squared on the left. So all of the r's will cancel, which is good because that was an added variable that I'm not allowed to have in my equation, and so I need to get rid of it. And what that leaves me with is Fs equals 2/5 ma. And now this is an expression for the static friction force, which I can use in the equation that I have up above, my F equals ma equation. And so substituting that in, I get mg sine theta minus 2/5 ma equals ma. All three of those masses are the mass of the solid sphere, and so I can cancel those out since every term has a mass in it. What I'm left with is g sine theta minus 2/5 a equals a. Since the 2/5 a and a are terms that both include a, then I'm going to go ahead and get those on the same side. And then I'm also going to flip the equation. So a plus 2/5 a equals g sine theta. 1a plus 2/5 a. 1a is the same as 5/5 a, and 5/5 a plus 2/5 a is 7/5. So 7/5 a equals g sine theta. There were several of you who got to this point and then made the mistake of saying that a equals 7/5 g sine theta. But we have to be very careful about how we write our final answer. Our final answer should be a equals 5/7 g sine theta. Right? Because I have to multiply both sides by 5 and divide both sides by 7 to get the final answer. And so the acceleration is 5/7 g sine theta. It's an equation that only depends on g and theta and that 5/7 out in front. So I could make an argument here by just comparing these two things that g sine theta, for no matter what the value of theta or g sine theta is greater than 5/7, some fraction of g sine theta. So that is some proof comparing those two, but what about the third one? We don't really have anything that talks about the hollow sphere yet. What I would say about the hollow sphere is this: the acceleration of the hollow sphere. We could go through a derivation like part A that shows that the hollow sphere is going to have some fraction g sine theta for the acceleration, and I don't really know what that number is. It wouldn't take too much time in order to figure out what that actual value is, but what's most important is that you know something fundamentally true about this solid sphere and the hollow sphere. They have the same mass, they have the same mass and the same radius, but they have different mass distributions, and that's the only thing that's different about the two. The mass distribution of the hollow sphere is such that all of its mass is on the edge, the furthest away from the axis of rotation, but the solid sphere has some of that mass more close in toward the axis of rotation in a uniform mass distribution. So the solid sphere has some mass that's closer to the axis of rotation, so it's going to be easier to roll, and that's why in the given values the moment of inertia of the solid sphere is less. And so you could make an argument that the hollow sphere has a larger moment of inertia because of its mass distribution, and because of that larger moment of inertia, it's going to be more difficult for it to rotate, and if it's more difficult for it to rotate, then it's going to have a smaller acceleration going down that inclined plane. I think that's enough in terms of comparing the two spheres. So the moment that you can say in your paragraph, because of the mass distribution and consequently the moment of inertia, the hollow sphere will have a smaller acceleration, it's not going to beat the solid sphere. So you've ruled out the hollow sphere by saying that. After that, you only need to compare the solid sphere to the cube. And you can say that because of the net force on each object, and my derivation in part A, the solid sphere has an acceleration of 5/7 g sine theta, and the cube has an acceleration of g sine theta. Therefore, as I stated previously, the object with the largest acceleration will get to the bottom of the ramp first, and the object that has the largest acceleration is, of course, the cube, g sine theta. And so I'm trying to make sure that I'm not leaving any holes in my argument. I really need to make sure that I talk about the solid sphere, the cube, and the hollow sphere. Don't want to leave any of those out. And then you've got to attack it with something that actually works. So if you start talking about some other things, like conservation of energy, they're wonderful arguments, and I didn't talk anything about energy here, but if I give a conservation of energy argument, I need to make sure that I'm saying the right things. The types of things that I would say for a conservation of energy argument is I would say when these three objects are at the top of this inclined plane, they all have the same amount of gravitational potential energy. Okay? Because they all have the same mass, they're at the same height, and g is the same. So they all have some gravitational potential energy that's equal to mgh. If they all start with the same amount of energy, but some of them have to rotate in order to get down the plane, then some of that rotational kinetic energy is not going to help it translate down the plane using translational kinetic energy, and so in that sense it kind of uses up some of that initial gravitational potential energy to rotate. And so instead of having more kinetic energy, it has the same amount of kinetic energy, but some of that kinetic energy is rotational kinetic energy, which doesn't help it translate. And ultimately, by writing a couple of equations, you could write down one or two conservation of energy equations for the sphere and for the block and show that the final speed of the block versus the final speed of one of the spheres is going to be much greater for the block. And then you still have to make a statement about if the final speed of the block is greater, why that means it gets down the plane faster. If it has a final speed that's greater, that must mean that it was speeding up faster. right? If it's got a greater speed when it gets to the bottom. And if it's speeding up faster, has a greater acceleration. And that takes me back to my first point of objects with larger accelerations will get down the plane faster. Okay? I think that about wraps it up with the paragraph. Just make sure that when you're asked these paragraphs, that you're to write these paragraphs, that you're really framing the question, right? When they ask you which one's going to get to the bottom of the plane first, decide in your mind what quantity is it that determines how fast it's going to get down the plane. Is it the final speed? Is it the acceleration? Is it the net force? Those are all acceptable answers in terms of approaching this paragraph, but you need to make sure that you have a clear goal and that you state that in the paragraph, and then give me some supporting evidence. Write a couple equations that you think are relevant, apply them to each object, and then tie all that stuff together so that way you've got a paragraph that makes some sense.